Welcome to our lecture on second-order linear homogeneous differential equations. In this video, we'll learn how to find the general solution to these important equations which appear frequently in physics, engineering, and other applications. Let's start by understanding what a second-order linear homogeneous differential equation looks like. The standard form is y double prime plus p of x times y prime plus q of x times y equals 0. Here, p of x and q of x are functions of x, and the equation is called homogeneous because the right side equals 0. In this video, we'll focus on the constant coefficient case, which is extremely important in applications. In this case, our equation simplifies to y double prime plus a times y prime plus b times y equals 0, where a and b are constants. To solve this equation, we'll try a special form of solution. Let's try y equals e to the power of r times x, where r is some constant we need to determine. When we substitute this into our differential equation, we get the following. R squared times e to the rx plus a times r times e to the rx plus b times e to the rx equals 0. Since e to the rx is never 0, we can divide both sides by e to the rx. This gives us the characteristic equation. R squared plus a r plus b equals 0. Solving this quadratic equation will give us the values of r that make our trial solution work. Now, there are three possible cases for the roots of this quadratic equation. Case 1, the roots are distinct real numbers. Case 2, the roots are equal a repeated real root. Case 3, the roots are complex conjugates. Let's examine each case and see what the general solution looks like. Let's start with case 1, where we have distinct real roots. If R1 and R2 are the two different real roots of the characteristic equation, then the general solution is y equals c1 times e to the r1x plus c2 times e to the r2x, where c1 and c2 are arbitrary constants. For case 2, where we have a repeated root, if r1 equals r2 equals r, then the general solution has the form y equals the quantity c1 plus c2 times x, all multiplied by e to the rx. Notice that we need a second linearly independent solution, and in this case, it's x times e to the rx. Finally, for case 3, where we have complex conjugate roots, if r equals alpha plus or minus I beta, then we can use Euler's formula to express the solution in terms of real functions. The general solution becomes y equals e to the alpha x times the quantity c1 times cosine of beta x plus c2 times sine of beta x. Now, let's look at some examples to see how to apply these techniques. Example 1. Let's solve y double prime minus 5 y prime plus 6 y equals 0. The characteristic equation is r squared minus 5, r plus 6 equals 0. Using the quadratic formula, we find that r equals 2 or r equals 3. Since these are distinct real roots, the general solution is y equals c1 times e to the 2x plus c2 times e to the 3x. Example 2. Let's solve y double prime minus 4 y prime plus 4 y equals 0. The characteristic equation is r squared minus 4, r plus 4 equals 0. This can be factored as r minus 2 squared equals 0, so r equals 2 is a repeated root. Since this is a repeated root, the general solution is y equals c1 plus c2x times e to the 2x. Example 3. Let's solve y double prime plus 2 y prime plus 5 y equals 0. The characteristic equation is r squared plus 2, r plus 5 equals 0. Using the quadratic formula, we get r equals negative 1 plus or minus 2i. Since these are complex conjugate roots, with alpha equals negative 1 and beta equals 2, the general solution is y equals e to the negative x times c1 times cosine of 2x plus c2 times sine of 2x. To summarize, we've learned how to solve second-order linear homogeneous differential equations with constant coefficients. Here's the step-by-step process. Step 1. Identify the equation in the form y double prime plus ay prime plus by equals 0. Step 2. Form the characteristic equation r squared plus a r plus b equals 0. Step 3. Find the roots r1 and r2 of the characteristic equation. Step 4. Write the general solution based on the nature of the roots. For distinct real roots, y equals c1 times e to the r1x plus c2 times e to the r2x for repeated real roots, y equals c1 plus c2x times e to the rx for complex conjugate roots, y equals e to the alpha x times c1 times cosine of beta x plus c2 times sine of beta x. These solutions form the foundation for solving many important differential equations in physics, engineering, and other fields. Thank you for watching this video on second-order linear homogeneous differential equations. In the next video, we'll explore how to solve non-homogeneous equations where the right side is not zero. Until then, practice solving these equations to build your confidence and understanding.